Okay, I want to take this from yet another angle and posit yet another assumption that, if valid, I proclaim will validate the continuum hypothesis. Now, this is a very controversial assumption that very justifiably a lot of you will disagree with. We've all been taught that anything times 0 is 0. However, I maintain that that will only work with numbers in the countable number set. In other words, let's just say that 0 times b will be 0 because b is any, let's take any natural number, 1, 2, 3, 4, 5, 6, 7, 8. Any number, any of those numbers times 0 will be 0 within the countable number set. All the way up to Aleph Nought, that will continue. Any number 0 times b will be 0. What about those values within sets of countability higher than Aleph Nought, such as Aleph 1, Aleph 2, Aleph 3? What would 0 times those numbers be? I believe that this would be an impossible question. I think that you could not posit this even as a question because Aleph 1 is not discrete, nor is Aleph 2, Aleph 3, Aleph 4, nor would the continuum or any level of countability higher than that. Okay, Aleph 1 is not bound by the discrete number system, which would have as its foundational basis 0 and 1. Because if you think about it, the discrete number system can boil down to binary numbers, so 0 and 1. Something either exists, which you could match as being 1, or it does not exist. And if we think about our discrete steps, they do boil down to 0, which you can think of as being the base of the step, and then 1, which you can think of as being the leap that we would make on the step. Okay, so discrete number, that's not the best way to put it, but any discrete number system would, in a sense, be binary. Since our Aleph 1 is not discrete, there really is no 0 times Aleph 1 in my argument. That would be my argument that I'm going to put forth. I understand this one will be controversial, but hang with me on this one. Okay, notice that 2 to the Aleph Nought can really be the same thing as 2 times 2 times 2 times 2. Aleph Nought times, there should have been an equal sign here, but you understand what I'm trying to say. 2 times 2 times 2 will arrive at 2 to the Aleph Nought, and that will arrive at C. Now, we're going to assume for the minute that there is an Aleph 1 between Aleph Nought and C. Okay, so this Aleph 1 is going to be a level of countability again between Aleph Nought and C, and we're going to see if the existence of such an Aleph 1 stands up to our initial assumption here. Now we're going to have to consider it in two possible cases. One where Aleph 1 is constructible along this line here of 2 times 2 times 2, if we can construct Aleph 1 that way, and one where we can't. Okay, so we're assuming here that Aleph 1 is constructible along here, and that Aleph 1, 0 times Aleph 1 is impossible, that it will not give us an answer. Okay, so we have 2 times 2 times 2 times 2 out to some place system getting us Aleph 1. Now I know what you're thinking. Oh, wait a minute, that a finite place system wouldn't get us Aleph 1. An infinite, if we had Aleph Nought as a place system, that would get us C, so what could possibly get us Aleph 1? I'm not worried about that right now. I'm assuming that Aleph 1 is constructible along this 2 times 2 times 2 times 2 going on to some level that would get us Aleph 1. Okay, well, I also can construct 0 by multiplying 0 times itself. We're going to call this number y, by the way. So 2 times 2 times 2, y times will get us Aleph 1. Never mind what y is, it's not important now. Okay, 0 times, well it is, but it's not important for the sake of this argument. 0 times 0 times 0 times 0 out to y will get us 0. Well, you notice that our 2's correspond to our 0's, and so at each point along here, 2 times 0 is 0, 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 all the way out to y, accountability of y. Now y is less than Aleph Nought. And so, since y is less than Aleph Nought, really, if we can establish a countability of a 0 and 2, essentially what we've done is cancel out our 2's every step of the way, and we have a 0 times Aleph 1 is 0, according to this argument. Now y, again, is less than Aleph Nought. So we're almost really saying that y is less than something infinite. We may not say that y is finite, that there may be an argument that there's a number neither finite nor infinite, but it definitely is not infinite. And therefore, if we can establish a one-to-one countability of each of these zeros with these 2's, we are essentially saying that if we multiply our 0 times our Aleph 1, that will get a 0. But that would contradict our initial assumption here, that 0 times Aleph 1 is impossible, that it will not get a 0, that it's something that does not exist. Now, stop.